directing it to the building's HVAC system. So basically.
Okay. So welcome everyone. I'm very excited to introduce Zeyneb, who's going to be talking about GeoMicroDistricts. So Zeyneb is the co-executive director of HEET, which led a recent large volume gas leaks study and is currently leading this initiative for GeoMicroDistricts as an innovative solution for transitioning from gas to heat pump energy. And so please try to stay muted throughout the presentation. If you have any questions, go ahead and put them in the chat, and we should have some time after the presentation for some Q&A. So Zeyneb, please go ahead.
Right. Well, I am going to use slides. I think visuals are very helpful in explaining something. So I'm going to just share screen for a second. Here we go. Let me know when I get it right. All right. So can you now see a very basic slide with a big orange band?
Yes.
Awesome. All right. So I'm really glad to be here. I will try to do a kind of skimming over the top explanation of the whole idea, and then have time for us to talk. I am a little on the tech geeky side. I will try to skip that stuff, but if you want to ask me about it, I'll be happy to answer. So HEET is a small nonprofit, and I'm going to come back to that nonprofit part. So we don't accept money from the gas industry or from the geothermal industry now, and try to maintain our independence. We're funded by foundations and personal donations. So, and our goal, above all, is just carbon emissions now by driving systems change. And that systems change, of course, includes all of the elements of a just transition as well. And we got involved in gas because of the leakage problem. We have a lot of old pipes. This is Boston leaking. You've probably heard about it. You've probably seen the signs on gas leaks taggings and engaged with mothers out front. We launched that by launching maps of the gas leaks in Massachusetts. And we continue to do that. There are now updated GIS maps for each of your towns. And we have more data, including your town's lost, not accounted for gas, and thus gas leak related carbon emissions. But along the way, we discovered that the state's current solution to these gas leaks was to replace all that old leaking, crumbling really, gas pipes, and that we were doing it at an enormous cost. A recent economics clinic estimated it at roughly $16 billion. And that gets amortized on us, the gas customers, over 40 years, which is long past when all of our climate plans say we can't be using it. So we're basically digging a disaster into the ground, digging stranded assets into the ground. And our plan for the gas system and our plan for climate are like two trains going down the tracks of the opposite direction, and we're heading for a crash. So at the same time, I assume a large number of the people in this room are depending on the gas system for their heat, and heat matters in New England. And so the collective impact of a large utility is quite enormous. And I understood that more and more year by year. And so the importance of a very, very planned transition and not allowing a collapse. I can't say enough for that in terms of equity. The people who will bear the burden of rising gas prices in a collapsing system are probably not living in Lexington. And that's something we have to think out as a state, as a society. And the good news is that, unbelievably, because this shocked me, we've actually seen a lot of strange innovation in the gas system. Back in the 1950s, we replaced every gas appliance in a short order. There were millions of gas appliances replaced in the course of 3 years in the 1950s to switch from coal gas to, quote, natural gas, which is now fracked gas. And these transitions have happened kind of quietly. Right now, the gas industry realizes that it is facing another transition. And the solutions they're starting to put on the table are things like renewable gas and hydrogen. And I'm just not even going to bother talking about the enormous problems and the regrettable substitution of moving this way, but it is an indication of their limited options going forward. So we approach the challenge of what do we do with this impending crisis with these design principles. We wanted something that was safe, renewable, resilient. I'm not going to read it, but all of this, and people laugh when they see this list, like, yeah, that's sure, we all want that. And for that safe part, we just ignored the entire explosive gas set of options, and went back in time again. I love that they used to give out medallions for electric homes. Like, this is not brand new, this idea. And heat pumps aren't brand new either, which is the only way to electrify heat. We don't have any other non-explosive heating options. And we live in the Northeast and we need heat. So it's a heat pump. And they're not new technology. You have one in your refrigerator. Hopefully your refrigerator doesn't look quite like that. But and basically, they act like a sponge for heat. It's the easiest way to think about a heat pump. You don't really have to understand it. They act like a sponge for heat. They take little bits of heat, suck them up, and move them over. So your freezer is taking heat and moving it out of the freezer to keep it cold. And you can do the same thing for your whole house. And now we have really improved heat pumps: air source, ground source, water source. Next. And each of them have different efficiencies. So how much electricity does it take to do that work of moving heat? And a geothermal heat pump, which uses the ground's temperature to exchange heat, versus an air source heat pump uses the air's temperature to exchange heat, because the ground stays more stable and you don't have to deal with the wild temperature swings of the air. You get a more efficient heat pump if you use ground source. And you can see this little diagram: 1 unit of electrical power from the grid, you get 4 units of free energy from the earth, and you end up with 5 units total. So it's a 500% efficiency, which is pretty unbelievable. Actually, it's kind of like magic. And so to date, and in the climate plans that we're dealing with one small exception, we're looking at, okay, if we're going to electrify and we're going to get off carbon, we're going to have to go to air source and ground source heat pumps building by building. And I just want to start by saying that is awesome and amazing, and we are ready and we have the technology. And I'm also going to say that this creates a very large burden on our electric grid, which is part of our planning needed. It has a really serious challenge in access, because it costs money to transition. And Barrett mentioned that with the need for subsidies. Our buildings are not ready for transition. Our checkbooks may not be ready for transition. And on top of this all, it requires a fight to the death with the gas industry, which can happen legislatively, but it requires their collapse. And in the collapse, as I mentioned, that's messy. And the workers end up out too. And so we didn't see it as ideal. And it didn't fit all of our design parameters to take down the gas system segment by segment and switch them to individual building heat pumps. And part of it is this. This top graph, I apologize for the quality of this graph, but is air source heat pump, the increase in electric power demands. And remember, we're currently attempting to make our electric supply green. And we need to do more wind and solar, but we'd have to do multiple times more in order to cover all of our heating and cooling this way. Ground source heat pump, because they're more efficient, is a little less. But there's these others down here that cost us even less electricity, and that's what we're going to talk about today. And that is networking heat pumps. So this is what we came up with as a solution by putting a row of geothermal boreholes in our public right-of-way. So I'm going to step back 1 second. So one of the challenges of that most efficient heat pump, the ground source heat pump, is that you need space to put it in, and it costs more upfront. And so by looking at and then we have that challenge of the gas company fighting to survive. So we put those together and we say, okay, gas company, forget gas. Take your rights of way in the street and your customers and your ability to dig up our streets and put in ground source heat pumps in our public rights of way. And so they'd install boreholes, as you can see, down the street, connecting them with a kind of shared loop. You could call it a thermal highway, you can call it a shared water loop. There's just water in the system. And then each of these has a service line delivering to the building a loop of water. And the water is at basically ground temperature within a temperature window. So the heat pump that's in the building is pulling the temperature needed for the building, heating or cooling, or both simultaneously, off of that and directing it to the building's HVAC system. So basically, the utility becomes a renewable thermal utility and delivers temperature instead of delivering an explosive gas. The loop of water is centrally pumped, and there's a few other things, but I'm going to skip to the next. There we go. So when people hear the word geothermal, they frequently get confused, and it's geothermal's fault because it's one word with multiple different technologies. And I just want to preemptively clarify. A lot of people hear geothermal and think of geopower, which is going several miles into the earth to kind of hot lava and powering electric supply. And that's super cool. And you can do that really easily in Iceland and other places here, but that is not what we're talking about. And, you know, people sometimes get concerned with earthquakes. That is this, not what we're talking about. And then people think geothermal and they think of that single home install. You know, oh, you put some loops in your ground, you had a drill come, and now you have geothermal energy. And that one is here, and that's the one where we said it's awesome if you can do it. It's a high upfront cost and you need space. And so these ones on the left and right, they're the newer ones. This GeoDistrict over here, they're building some of these in Paris. Cornell just got permission, and it's going still really deep enough to get actually direct hot water and pumping it around in a district energy system. That's super cool if that's the right spot for you. What we're talking about over here is on the right. Novel, it is an innovation, not of components, but of the way you put the components together. And it's purple because it's not hot or cold, it's both. So the temperature it's accessing is the same as for the Geo Home. It's just the stored energy of the sun in the ground. It's not the deep earth energy. And it doesn't, in the drilling world, it's shallow. So I hope that clears up some questions. So the magic of interconnecting heat pumps is that you suddenly, you're able to share. You get economies of scale, first of all, because the main cost of geothermal is getting that drill rig to your house. You get load sharing. So if you live next to a convenience store that's using cooling, and that means they're dumping heat into the loop, you can then pick up that heat, and the net total is zero. It's a net zero. It's like a passive house community energy system. So if you have a street that has a kind of equal heating and cooling load, you don't even need the boreholes. You're just canceling out heating and cooling in that shared loop, which is a whole new kind of energy efficiency. It's kind of the sharing economy for energy. And the boreholes are pretty amazing because what they really are is their energy storage, which is exactly what geothermal is. The sun shines on the earth, keeps it kind of a certain temperature, and we're just accessing that. The reason it stays 6 feet down, is because our earth and our bedrock actually hold energy really well. So it just kind of levels out the energy, flattens it. So what we're doing is basically putting a big energy battery into our ground and then saying, okay, well, we're gonna store the energy from the heating energy from the summer when we're cooling, and then we're going to use it in the winter when we're heating. And so again, you're kind of canceling over an annual basis, which means that in sum total, you're using very little energy. So does this work? Because it sounds pretty good. So a couple of years ago now, we hired a global engineering firm called Bureau Happold to do a feasibility study for Massachusetts. And They took representative street segments for the entire state's gas system and modeled all of the energy, et cetera, et cetera. And found that it works as an individual single segment replacement in the majority of street segments. And then when the next step is when you interconnect these segments, can it cover the whole system? And that's what we're working on now. So the known and somewhat quantified benefits. So first of all, safety and health. It doesn't explode, water. And because you take combustion out of the house and out of your system, you improve indoor air and outdoor air. In the Massachusetts current electric supply, it would be a 60% reduction today and a 90% reduction by 2050. All of the carbon for the system comes from the electricity used for the pumps. And so if you are able to get to a totally green electric supply, this is also zero carbon. And then, you know, I'm not going to go into the details because I think I suspect I need to speed up. Resilient, reliable, scalable, adaptable. It gives cooling. We're going to need more cooling. We're in the midst of transforming from a heating climate to a cooling climate here in Middlesex County. It does a whole bunch of things for the electric grid. It can flatten the grid loads and provide the cheap energy storage we need. But I want to get to the last three, which is the question of equity. So as I've been going along, you could put it in the beginning as fighting utilities. I've discovered that there is one thing I have to give them. As far as I can tell, the utility of a utility is basically to share the cost of energy among all. And in essence, that's a little bit like socializing energy. So everyone has access and can afford access because you're sharing the cost of the infrastructure. And so that and the opportunity to keep jobs for people who need jobs and the opportunity to do it at a scale and speed that we need to get to our goals, those things, I think, make this a critical path. We have some data. There's a great case study in Colorado Mesa showing the energy savings annually. We have, the Bureau Happold study showing, I already mentioned the greenhouse gas reductions depending on your electric supply. This is a chart from Xcel Energy in Colorado showing the grid flattening, which if you're into the electric grid, that's pretty amazing. The workforce we've been working with for a couple of years, and we are working with the various unions involved. And they already have some of the skills and are certified, for example, for fusing HDPE pipe, the skills transfer. Equity. So again, that idea that every person can have access if you build an infrastructure, as opposed to having it go house by house, this transition. I feel like the transition has to be at that kind of scale. And so we lower the cost of energy. It costs less than heating with gas to heat with this networked geothermal system. And that was in our Bureau Happold study. And then both Eversource Gas and National Grid Gas have modeled it as well on their own. And it has come out less than the cost of gas to run the system and for heating with this system. And it includes cooling. And then the costs of transition get rolled into that amortization, so it's spread out over time and between people, making it more accessible. So that's why I actually stand by the idea of having the gas utilities transform themselves and build this geogrid. And they can do it one segment at a time. There's one GeoMicroDistrict going in, backing that gas system up, iterating, adding more segments until we have backed the gas system all the way up to the last point of contact and have a green geogrid. And what that would look like, this is our actual gas system. And actually it's kind of beautiful and really cutting edge in the 1800s, but it's time to reimagine it and begin to build something different. And what we can do is, there are some places where it does make sense to go to an individual heat pump. And for the gas system, they need to strategically ban, and they need to be told, okay, if it doesn't make sense, then you need to transition it off of your system as a utility. And we're going to have to do a lot of that. And then I'm going to acknowledge, there's a few places where we're still going to need to hold on and maintain until we get a solution. So we've been making a list of industries that don't yet have an electric solution, like glass smelters. And so there's some minimal strategic maintenance that, hopefully in 10 years will be hydrogen or something. And then the vast majority of our system has to strategically evolve over time in the next decade or two. And I believe we can do this on schedule. The first step is to put in initial installations. We have 2 approved and funded in Massachusetts. We're leading the nation. There's one $4 million allocation in the Merrimack Valley where the gas disaster happened that's going in. And the Eversource gas pilot has $10 million, and they are in the process of selecting a site right now if you happen to be in Eversource gas territory. National Grid has proposed an even larger pilot where they want to replace segments of their leak-prone gas system. And we'll come back to that because that is currently being heard at our Department of Public Utility. Oh, and if you have an idea for a pilot, there's a link down here. So location. So HEET is really committed to having this energy transformation seed that we're starting to grow be as open, transparent, data-based, and engaged with everyone as we possibly can. And so we are running and have all of the relevant agencies and gas utilities participating a monthly charrette process where we have topics and there's open information sharing between all different types of people with different backgrounds, and we try to find and fix challenges before they grow. And we're building a library of tools from that. We were part of designing a new piece of legislation called the Future of HEET, and it does all of the pieces that are needed to drive this transition rapidly. And I would be happy to go into this. We even have proposed a financial mechanism for funding the low-income household transition and the worker transition. To kind of, I'm trying to speed up so we have time to talk. So on the municipal side, here's some potential actions to help drive forward this novel path to decarbonization. So increasing education and information on the risks of gas and alternatives to gas. I know there's 2 other sessions with friends who are talking about gas health impacts and other gas system impacts. As a municipality, including your gas leak emissions in your greenhouse gas calculation is great. Expressing concern from your Department of Public Works and elsewhere with any kind of gas investment going in, understanding that that is no longer a wise financial investment and not fiscally responsible. Suggesting locations in your town or your own house for piloting, and pilot isn't quite the right word, but for initial installations of networked ground source heat pumps. Participating in the charrettes if you are curious or want to add your voice. And then there is this amazing opportunity in Massachusetts. We're one of only 4 states that is launched a statewide plan for gas. It's called DPU 2080, which is the docket number, very, very sexy name. So I just call it the Mass Plan for Gas. Testifying or submitting a letter in that process may be one of the most high impact things a municipality or an individual can do. And then of course, if you're in a national grid town, which I know Lexington is, the National Grid's request for a pilot transition off gas, it would be great to support that at the DPU, and that's going on right now. So if it wasn't clear, this is not just about technology. A just transition path to electrification using these geothermal or networked heat pumps, it involves people, and without people and households and family, we can't actually drive this kind of change. It's an enormous change at every level. And so for me, these are my people, these are my daughters. And yeah, it's a really cute picture because now the oldest ones are teenagers, and this one's more powerful. But this is why I'm doing this, and this is why most of us at HEET are, is that we don't want to leave it all up to them to solve the problems we've created. So, and we're really unbelievably happy that we have a solution like this to shepherd through and need all the help we can get. So I have a bunch of references and resources, and let's, I think the slides get shared, so you'll get these. And
Wonderful.
I think we did it fast enough. No?
We have a few minutes for some questions.
Sorry.
It's kind of a soft end at 11:30. So if you're happy to stay, people can stay on and keep answering questions. But we got a lot of great questions in the chat. I'll start with some of them. Is the viability of this solution dependent on certain criteria in the area you want to do this, or is it essentially possible anywhere?
Right. So it is essentially possible almost anywhere. The question is really a balancing of the cost for the location characteristics. So if your bedrock is less ideal and you have very minimal space, so you're going to have to do some very fancy drilling to get the distance you need for the water, and you've got huge energy use, then it may not be worth the cost. It may not make sense in that location. So it's really a constant calculation between various variables. So most of Massachusetts, with the exception of Cape Cod, is some really great thermal conductivity bedrock, pretty close to the surface. So we're lucky in that way. And you know, most of our streets, we can pull it off at a cost that would indicate a price of energy lower than gas.
Great. When you talk about commercial buildings that have cooling needs within a district, does this include refrigeration? Does the technology exist to hook commercial refrigeration into these systems, or are you just talking about air conditioning?
Oh, I'm talking about refrigeration. Absolutely. Yeah, there's nothing better than having a good ice rink or data center near a whole bunch of houses that want heating, because you just canceled out your whole energy demands. So yes, the technology exists. It's done. There's a bunch of case studies. Europe and China are really moving on this kind of idea of bidirectional ambient networks. In fact, we're quite behind in some ways. I'm going to go ahead and share one quick picture and answer. There we go. This is the Olympic, Olympic Stadium in China, Olympic Media Center. It has a heat pump under that dock, a titanium seawater heat pump. If you think about Boston, that's kind of fun. This was for a short few weeks the tallest building in the world, and it has 1,100 boreholes underneath the building footprint. There's a lot of stuff that has been done that we just have not applied or tried.
Great. How long does it take to build and install a system, assuming approvals are in place?
It's pretty quick. So Eversource's timeline to use them, and they're not like the slowest. I mean, they're not the fastest utility. They will put it in the space of a month, and they're going to go slow. And this is the first time. You can put all the boreholes into a street in less than a week.
Great. And is density a factor? Urban versus suburban versus rural?
Yep. Yeah, absolutely. So you're actually going to get a much more energy for your infrastructure, like per infrastructure, in a high density area, because you have the more diversity of loads and the more mixed use, the more you're canceling energy, and so you need less infrastructure for the total sum energy you're providing. So yeah, the mixed use and the density are big factors.
Great. Please feel free to continue to put questions in the chat, but I also see a few hands raised. So Brian, do you want to go ahead and unmute yourself?
Sure. This is wonderful. This is a great, very well thought out plan where we utilize existing labor forces and we go to a renewable solution. We keep a business in business while solving climate problems. My question was going to be, could you give us the best case scenario for sites to search for within our communities that could be best to do the first, pilot with the best chance of a positive experience? And you've done a good job of explaining kind of density, some of the concerns about the geology and so forth. But if you might give us like, you had in one of your graphics, you had shown kind of an area where the gas lines were pretty sparse, and that might be a good spot for them to begin. If you could kind of give us a quick summary of what a good pilot neighborhood would look like,
Yes.
so that we can all search for them and send them to you.
That sounds fantastic, and we have a site to submit them, and you're welcome to send them to me. And we just posted a site selection criteria checklist on our website. That was an outcome from our first charrette on site selection criteria. And it is, I mean, Eversource, we've got like I'll just describe briefly. There's a couple pilots. They want to make sure that there are low-income households. They want to make sure, so there's a difference between the physical site criteria and what you want in a pilot to make your point. And so they want mixed use, some existing buildings, some new buildings. So there's a spot in downtown Worcester, there's a spot in Framingham, there's a spot in Somerville, all of which meet each of those characteristics.
So there's a website I could find.
Yes, I will try to get the link and put it in the chat.
Thank you.
Great. Another question from the chat: is each building metered, or are fees based on building characteristics?
So that's going to be a fascinating big fight. We're actually going to have a shred on that. So some people are saying just do a gallons per minute, like it's not that different. Other people are saying that we need to do a flow meter, like gallons per minute. And I'm actually I think we're going to do BTU meters, and we're going to put them on the other side of the heat pump, between the heat pump and the customer. And the reason I think that is I think we're going to basically be building an interface between thermal and electric grids, and BTUs will be an exchange mechanism. By putting the meter on the other side of our heat pump, the heat pump becomes part of the gas infrastructure and is paid for by the amortization method, allowing the transition to go super fast. But come join the debate. We don't know yet.
Great. And a question I have that I think is maybe related to something this person is saying: will it be possible for people with boreholes on private land to sort of hook into this larger system?
Yeah, so any thermal source, you're saying, forget boreholes, you could hook up your air source heat pump, or any source of thermal energy. And if you start to look around you, we actually have thermal energy everywhere. You can make a thermal map of a town. London has done it. It's fascinating. They're now using some energy from their underground tubes to power things. Your water system is a source of energy. But I think the other thing I just want to come back to is, for the Eversource pilot, the cost per month for any participant for all heating and cooling is $20. If you are low income, it's $5. Those are pilot prices. They don't yet know how to price it, but it's a good deal. And the National Grid one is doing it differently. They're replacing all appliances and totally transitioning off gas. And they're trying to charge for the entire infrastructure up front in the first 2 years by charging participants $125 a month, after which you pay $4 or $5 a month, depending on who you are, going forward for all your energy.
Someone asks, is this analogous to community solar projects?
In the sense of coming together to share infrastructure, yes. But I think it has some advantages in that the reality is that our gas distribution utilities have a massive amount of financing capacity and customer infrastructure and power, basically, that can be leveraged, flipped towards this renewable energy path in a way that I think sometimes community solar projects struggle against some of those systems. But it is the same idea of sharing infrastructure.
Great. And could you talk about what role is there for sort of improved individual residences to make this more cost efficient?
I would really probably cry if they went ahead and put this infrastructure in without weatherizing and insulating the buildings. That would suck. You can do it, which is kind of interesting. You can go ahead and just make your system way bigger. I think this actually could be a driver for the kind of house by house electrification readiness that we have to have happen no matter what. And it's not easy, and everyone's ignored the electric capacity challenge, which I think is a really big one.
Great. I see another hand from Brian. Go ahead and unmute yourself.
Yeah, so that was my question, was the electric utility. There's transmission and capacity is becoming a large expense for them, and load control systems are of great value.
Yeah.
Hot water heaters, for example, get a lower rate for the utility to control when they charge.
Yes.
Those kind of systems and matching with the existing thermal storage could be of great value. Could they contribute to this transition?
Yes, and they are very interested. We're beginning to talk more to the electric side. Basically, if you're into the energy thing, this is a distributed energy resource that is non-intermittent. And so if you build a thermal grid, you have a non-intermittent load balancing mechanism that can just cut off the peaks of the electric grid, allowing you to expand your electric capacity far more rapidly without consequences. You get rid of all the peaking. And the way you do this is by shifting load from the power grid to the thermal grid. So if you know you're coming into a peak, you can have your thermal grid run all the pumps and raise up the temperature or lower down the temperature, whichever way you're going, hours beforehand, and then coast through the peak, shutting down all of the electric demand from the thermal grid.
Yes, there's a lot of phase change thermal batteries that are being talked about with like SunAmp in Europe and so forth. There's also ice energy is where they make a block of ice to coast through a peak event and provide air conditioning. So it's a good match with those technologies as well.
Absolutely.
Great. Another question, is there a way for communities to start asking their utilities for this technology?
Yes, absolutely. I suppose we should make a form letter or something. I think the most impactful way at the moment in Massachusetts, since we've already convinced all the utilities to pilot it, is National Grid is currently asking for permission from the Department of Public Utility. And by sending a letter of support from the municipality, that shifts the request to them requesting something that people actually want or towns actually want. And it does have an impact. The other piece is that hearing for the whole state on what happens to our gas utilities, weighing in on that, sending a letter for that also would be very high impact. And I also just think large numbers of requests and mentions in whatever meeting you ever have with your utility help. But honestly, the gas utilities, they have the most to gain from doing the switch. They know they're in trouble. I think that the challenge actually is the people. Like, I think that sharing this as not a loss of a system, but as a gain of something better is maybe the most important thing, that we can actually have better, more comfortable, safer, healthier energy for lower cost. We can basically build a better world.
Wonderful. I think that's an excellent note to end on. So thank you very much, everyone, for attending.